Hello, everyone. Welcome to the Algorithms channel. So we will have a series of videos aiming to explain the basics, fundamentals in algorithm design and analysis. The textbook that we'll be following throughout the course will be the Levitin's Introduction to the Design and Analysis of Algorithms book. And we start with a gentle introduction. Let me just share a couple of slides that I prepared previously. Okay, so I guess you all have an idea about what an algorithm is. It is in a very wide sense, it's a step-by-step procedure to accomplish a task. And the name comes from a Persian mathematician. So originally, he was from Uzbekistan, and from the 9th century, his name was Al-Khwarizm. So Al-Khwarizm, he is also known as the father of the algebra. He wrote some books when he was a professor at the House of Wisdom in Baghdad in the 9th century. So at that time, the House of Wisdom in Baghdad was an attraction point for scientists from the world. So there is an interesting link to what it is. So I just copied it here by the Professor Jim Al-Halili. So you see the Michael Faraday Prize lecture by him about the House of Wisdom, and he has a book on that. So Al-Khwarizm described the basic algebraic operations in a step-by-step procedure. And with his methods, anyone who starts with the same input following the procedure, following the algorithm, will end up with the same output. So that is the backbone of an algorithm. So in the later years, the methods developed by Al-Khwarizm was referred as Al-Khwarizm's method. Al-Khwarizms in time just converted into algorithms. And now we call this field as the algorithms. So that is, the algorithm is actually, this concept is way older than computers, but in the contemporary vision, so in computational perspective, an algorithm is actually a sequence of unambiguous instructions run by a computer on a given legitimate input. And algorithms is actually the core subject in computer science curriculum. So I would like to also add the data structures and discrete math. And those three courses, I think many of the professionals will agree on me that this is the core subjects in the CS curriculum. So it is a good habit to learn about the history of the concepts and the history of science. So I suggest you to have a look who Al-Khwarizm was and his contributions and why we call the algorithms with his name now. As far as I know, as far as I remember, until the 15th century, his book on algebra was the main textbook in the European universities. Anyway, so in an algorithm, so we have a problem and we would like to solve a problem. This problem is a computation or a calculation of something. So you have a method to do this, and this method will run on a computer, as you see on this figure. So there will be an input, the instructions will be executed, and you will have the output. So that's it. Important points are, so for a problem, there might be different algorithms to solve it. And even for a single algorithm, there will be different implementations. So this brings the natural questions: which algorithm is better and which implementation is better than the others? And we will be focusing on these questions on the upcoming lectures, but just to motivate for the upcoming lectures, it is an important question to find the right algorithm with the right implementation. Okay, so here is a Here is a classic example when we teach the algorithms. So assume the problem is you would like to find the greatest common divisor of given two integers m and n, and you need to develop an algorithm for that. So there might be several of them, but here we see three possibilities. The first one is you can check all the possibilities. So I'm given two integers m and n, and I'm looking for the greatest common divisor. I will start from the smaller integer and then check everything down to 1 and see if it works. So let's make an example. So let's say I'm trying to find the GCD of, let me say, 45 and 18. Okay, so it will be something less than 18. So I start with 18. So with 18, 18 divides 18, but 18 does not divide 40. 15, 14, so down, I will see that at point 9, 9 divides both 18 and 45. So I can say that, okay, so this is 9 because I started trying 18, 17, 16, and 9. So yes, that is bingo. So that's checking all possibilities. And this is an algorithm. When you're given two numbers, start with the smaller one. So check if it divides both of them and just continue down to 1 and stop whenever you have you have the correct division. Okay, so this is algorithm 1. So another algorithm might be using the prime factorization. Actually, we learned it in the middle school, right? So we say that, okay, so 45 is equal to 9 times 5. Actually, it is 3 to the power of 2 times 5, and 18 is again is equal to this one. So we go and find the common primes, and then we say that, okay, so 9 should be the answer. Okay, so that's by the prime factorization. And yet there is another method with the Euclid's method. So Euclid said that, okay, so the greatest common divisor between m and n is equal to the greatest common divisor between n, the second component, and m mod n. I into details of the proof that that works, but it works. So let's try to do it with this Euclid's method. So if you say GCD 4518, then this is equal to GCD 1845 mod 18, which is equal to GCD 18 and 9. Okay, and if you do the same trick, so GCD 9, 18 mod 9. So we see that 18 mod 9 is equal to 0. Whenever you reach 0 in the second term, the first term gives you the greatest common divisor. So the greatest common divisor with the Euclid's method is again 9. So we have different algorithms. Surely it needs an analysis to find out which one is better, which one runs better than the others, but we will be talking about them in the upcoming lectures. Just I would like to mention here an interesting case. What will happen if you would like to compute the greatest common divisor between two integers? So let me say it is 45, and now it is 0. Okay, so with 45 and 0, then with the Euclid's method, you will immediately say that the greatest common divisor is 45. However, if you would like to run the algorithm 1 and algorithm 2 with this GCD 45 and 0, so you will encounter some difficulties in the first two options. So that means while defining the legitimate input for the first two algorithms, we need to have a special processing for the case when one of the integers is equal to 0, right? Because you cannot make the prime factorization of 0. And here, if you would like to check all possibilities and start from the smaller one, so that will be a failure for the first one. So for the first two algorithms, the input space either should not include 0 or should have a special processing. So I would like to just mention this because it is important to define the input that the algorithm will be seamlessly running on while designing an algorithm. And we'll be focusing on these aspects in the upcoming lectures. Okay, anyway. Okay, so let me just clear these drawings and continue. Okay. Whenever we have a problem, so we would like to develop an algorithm for that, and here is a step-by-step guide to design an algorithm. Surely it's very rough, so the first step is understanding the problem. That is crucial, so we would like to understand what is the input and what we would like to compute, and this is understanding the problem. And once we understand the problem, before designing the algorithm, we should also have a look to the computational device on which our solution will execute. Okay, so usually in the algorithm design textbooks and everything, so we assume that this computing device is a computer built upon the von Neumann architecture. So what is the von Neumann architecture? Maybe you know from the previous courses. So there is a central processing unit, and this central processing unit is connected to a memory. And whenever you would like to execute a program, what happens is you read data from this memory, which is a random access memory, which means you can just read every point from that memory in words. So that is why we call this the word RAM model, okay? In words, and then once you read the data from the memory, so you can run the instructions. So in the classical von Neumann architecture, we assume this is a sequential execution, which means the instructions will be executed one by one. Okay, so there is no parallel execution, there is no parallel instruction execution, but actually it is a bit different in today's architectures, but for the sake of easy understanding, so let's at this point continue with the sequential execution. Anyway, so while also examining the properties of the computing device that we'll be using on. So what we will do is we will decide on which algorithm design techniques we will use, and then design our algorithm. So once we have this algorithm, so that means actually you have not coded anything, you have not implemented anything. You only have a pseudocode. A pseudocode means step-by-step procedure, a recipe that defines how we will go to the output, how we will compute the output. Okay, so that's just a pseudocode. And then once you have this pseudocode defining your algorithm, we should do something very crucial. Okay, so we should prove that this algorithm is correct, which means it does the job on any valid input. This is something very important because this is why we call this an algorithm. An algorithm has a correctness guarantee, okay, has a performance guarantee. We will see that later, but for the time being, it should be correct. It should be correct on the assumed valid input space. If it sometimes works and if doesn't work at some other times, that might be a heuristic at best, but so correctness. Then efficient. Efficient simply means fast. lot of resource. Resource generally refer to memory. We don't want an algorithm to be memory hungry. Okay, so we would like to use enough space and we would like to compute the result as fast as possible. So that brings an analysis. So we will analyze our algorithm and see how see the effectiveness of this designed algorithm. Okay. At that point, there are some questions we will need to answer. The first one is, okay, so you have a problem, you developed an algorithm, and would it be possible to develop another algorithm better than yours? Okay, so that means, is the solution you devised is optimal? Okay, so now an optimal solution means, okay, so this is the best way to compute it. Okay, so there cannot be any other ways that is better than your design, your algorithm. Okay, so this is called the optimality. And it's not always very easy to prove that something is optimal. But once you prove that your algorithm is correct and it is optimal, then that is something really nice. So the next step will be to implement it with the best software engineering practice. Okay. One point maybe I should also mention here is, so we are developing algorithms for problems, and that also brings this question, are all problems solvable? Maybe I should revise this question. Are all problems solvable efficiently? So there are some very hard problems, and there are even some problems that we cannot solve. And so that is another area in the algorithms, but it is not for the fundamental basic undergraduate study. So that's for the graduate courses. But we will be spending some time on these hard problems, maybe in the upcoming lectures late in this semester. Okay. By the way, here I also included a book. So that is a book from the 50s, so by the famous mathematician George Polya, and the name is How to Solve It. I find it interesting, and I thought maybe you might be interested in looking for more resources to have a better analytical thinking scheme. Actually, George Polya defined a 4-step procedure to approach the problems, and it is a nice book to have a look if you would like to go further. Okay, so that's the general sketch in the algorithm design. Okay. And sorry. Yes. So the last point that I would like to talk to you in this first introduction is the major areas in algorithms. Okay. So if it needs to make a classification among the algorithms, actually, these are the areas, research areas in algorithms. I can list a couple of them. So the first one is the sorting algorithm. Sorting is very crucial in computer science. In 60s, when Donald Knuth was writing his book, The Art of Computing, there was a statistics. So it said that, okay, so around 1/4 of computing time on all over the world, it is devoted to sorting. So that means, if it translated to today's word, I think it will not change much. So 1/4 of all the computing power at this time, they are somehow sorting something. So sorting is that much fundamental. So it is a backbone in many algorithms. It is a very important piece that is used in many algorithms. So sorting algorithms is a major area in algorithm design and research. Similarly, there is the searching. So actually search and sort, in my personal perspective, covers maybe 80% of many tasks in computation. So searching something in a big database or a collection, something. So these are called the search algorithms. So there are similarly the string algorithms that focus on one-dimensional data, and the graph algorithms. So that is a huge area in the algorithm development. So the combinatorial algorithms, similarly, the geometric algorithms focus on the geometry, for instance, the convex hull problem, something like that. And then we have the numeric algorithms. These are mostly the approximations, because sometimes you cannot compute something exactly, but you will need to make an approximation to it, and you might need some numeric algorithms. Actually, we will have examples of all of them in the upcoming lectures, but that is just to give you an idea about which type of algorithms we have in general. Okay, and if we would like to develop efficient solutions to computational challenge, then we need a solid grasp, solid understanding of algorithms and data structures. That is essential. And with that purpose, actually, in the upcoming a couple of videos, we will be visiting the data structures. I know you know them already, but just to make a recap and a quick summary of the data structures on the upcoming lectures. Thank you very much, and see you in the lecture. Take care.